Okay, so we're going to have a look at another question from the topic of ordinary differential equations. Ordinary differential equations. Alright, so the question we're going to have a look at is we're going to try and find a general solution. So we're told to solve. The equation that we're being told to solve is y double prime plus x times y prime plus y is equal to 0. And we're told to solve this under the assumption that y equals the sum from n equals 0 to infinity of a n times x to the n is a solution. Okay, so this is what's known as a series solution differential equation. So we've seen quite a few differential equations at this point. Usually the differential equations we've dealt with do not have non-constant coefficients. So this has an x value as a coefficient, so we have to be a little bit more careful when dealing with these. So here we're going to assume y equals this sum is a solution. So we'll start by saying y equals the sum from n equals 0 to infinity a n x to the n is a solution. We're going to take the derivative. Y prime of this is the sum from n equals 0 to infinity of n times a n times x to the n minus 1. This is how we take a first derivative here. And then we need a second derivative. Y double prime is equal to the sum from n equals 0 to infinity of n minus 1 times n times a n times x to the n minus 2. Now you notice all of these are a sum from n equals 0. They don't have to be. We could at any point change these to the sum from n equals 1 and n equals 2. So this could be n equals 1, this could be n equals 2. Because when n is 0 in this expression, it goes to 0 anyway. So the sum from n equals 0 will be identical to the sum from n equals 1. Now we need to substitute these into our equation. So we find that y double prime plus x times y prime plus y equals 0 becomes 0 is equal to y double prime, which is the sum n equals 2 to infinity n minus 1 times n times a n x to the n minus 1 plus x times y prime plus x times the sum from n equals 1 up to infinity of n times a n times x to the n minus 1 plus y, which is the sum from n equals 0 to infinity a n x to the n. So this whole thing, this is equal to 0. This term in the middle, the x times term, we can actually shift this. We can factor this x into the x inside the sum. So this will give us 0 is equal to the sum from n equals 2 to infinity n minus 1 times n times a n times x to the n minus 1. We will have plus the sum from n equals 1 up to infinity times n times a n x to the 1 times x to the n minus 1 is going to be x to the n. And then we're adding this to the sum from n equals 0 up to infinity of a n times x to the n. So now we've factored that non-numeric coefficient, that non-standard coefficient in. So now we have a series of sum terms. What we're going to try and do at this stage in the equation is we're going to try and combine these sum terms in order to get a recurrence relation. And we have to be a little bit careful here. We have to try and adjust the powers so that they're all the same. And this will create an expression for us in terms of the powers. So if we look at the term up the top, we're just going to look at this term. This term has an x term which is x to the n minus 1, we need that to be x to the n. So we can say sum n equals 2 to infinity times n minus 1 times n times a subscript n x to the n minus 1. The way we could make that power equal to 1 is by letting n minus 1 equal k. So this would tell us to let n equal k plus 1. So this will give us the sum from k plus 1 equals 2 up to infinity of k plus 1 minus 1 times k plus 1 times a to the k plus 1, a subscript k plus 1 times x to the k plus 1 minus 1. If we simplify all of this, minus 1 from both sides here, cancel these, this becomes the sum from k equals 1 to infinity of k times k plus 1 times a to the subscript of k plus 1 times x to the k. And then what we're going to do is we're going to let k become n. So we're going to just change the variable here. And this then becomes the sum from n equals 1 to infinity of n times n plus 1 times a to the subscript n plus 1 times x to the n. So what we've done is we've shifted that power by shifting the summation, right? And this is how we did this. We used a substitution where we let n equal k, and then at the end we swapped k for n. Because once we changed the n, once we said that n minus 1 equals k, this implied that n was equal to k plus 1. What we had done is we had changed from n to k. But k is just some term. So once we had that simplified in terms of k, we can just swap the k for an n. It's still just some term. So this is allowed. Right? So it's a slightly unusual process, but it is an acceptable process. So this implies that 0 is equal to this sum from n equals 1 to infinity times n plus 1 times a subscript n plus 1 times x to the n, plus the two terms we had here. So this is plus the sum from n equals 1 to infinity of n times x to the n, n times an times x to the n, plus the sum from n equals 0 to infinity of a n x to the n. Sum from n equals 0 to infinity of a n x to the n. All right. So now we have these three sums, and we can all let them go from 0 if we want. Conveniently, they all contain an x to the n. So if we let this one go from n equals 0 and this one go from n equals 0, this actually doesn't really create any problems for us. We don't need to, but we can if we want. So now we're going to factorize this. This is going to tell us that 0 is equal to x to the n times the sum from n equals 1 to infinity times n plus 1 times a n1 plus the sum from n equals 1 to infinity of n times a n plus the sum from n equals 0 to infinity times a n. So now we have a factored expression. So either x to the n is equal to 0 or this expression is equal to 0. And so we are going to say that the sum from n equals 1 up to infinity n plus 1 times a to the n plus 1 plus the sum from n equals 1 to infinity of n plus the sum from n equals 0 to infinity of an, this is all equal to 0. Now this is only valid for integers. So we're only thinking about n is 0, n is 1, etc. So if we run these all from n is 0, if n is equal to 0, we find that the first two terms don't count because they go from n is 1. Then we have n is 0 up to infinity. We have a of 0 is equal to 0. So we're told a0 is equal to 0. If we let n equal 1, we find that the first term becomes 1 times 2 times a2 plus 1 times a1 plus a1 is equal to 0. So this tells us that 2a2 plus 2a1 is 0. 2a2 plus 2a1 is equal to 0. So this implies that a1 is the negative of a2. So we've got that a0 is equal to 0. We have that a1 is equal to negative a2. And now we're going to keep doing these. So we're going to do n is equal to 2. This gives us 2 times 3, which is 6, times a2 plus 1, which is 3, plus 2 times a2, 2 times a2, plus a2 is equal to 0. So now we have, this implies 6 a3 plus 3 a2 is equal to 0. If we move, let's say a2 to the other side, we're going to find that we get 6 a3 equals minus 3 a2. If we divide both sides by minus 3, this will tell us a2 is equal to minus 2 a3. So now what we're doing is we're building up a series of terms which relate each term to the other terms, right? We're finding that a0 is equal to 0. We are finding that a1 is equal to negative a2. We're finding that a2 is equal to minus 2 times a3. But we found out that a2 was negative a1. Right? a2 is negative a1, which means when we get to this step, we can think about this as, we can think of a3 in terms of a1, or we can think of a2 in terms of a1 if we want. Right? These are relations we're getting between these terms. So a0 is 0. We're told a1 is the negative of a2. We're told a2 is negative 2 of a3, and so on. Now our initial solution was of the form, so initial solution was of the form y equals the sum from n equals 0 to infinity a n x to the n. Now this is of course a polynomial. So this means our original solution was of the form a0 plus a1x plus a2x squared plus a3x cubed, and so on. And so now we're starting to find relations between terms here, right? So if we rearrange the a2, we can say a2 is actually minus 1a1. So we have a0 is 0. We have a1 is a1, so this is a1 times x. a2 we worked out was minus a1, so this is minus a1 x squared. a3 we know in terms of a2, so this is a3 is equal to minus a2 on 2, but we know that a2 is minus a1, so this is a1 on 2. So we've got a1 times x minus a1 times x squared plus a1 on 2 times x cubed, and so on. If we factor an a1 out of this, we get a1 times x to the 1 minus x squared plus 1/2 x cubed. Then it will be a minus the next term, and so on. And this is a general solution for this particular differential equation. So this is our general solution. Therefore, y equals some constant times the series x minus x squared plus 1/2 x cubed minus so on is a general solution. Now in this case, we don't have a full form of the actual solution. We haven't actually found what series this converges to. We have just said that this is some series, right? So often when we're doing these, not only will you find this list of terms, you will also convert it to a particular known Taylor expansion of a series. In this case, for this introductory one, we're just going to leave it in this form, right? We were just told to solve. We were told that this is a solution, and we're told to find a general solution. This is a general solution in this case.